Вы гляньте, ну, начало, да, мы загрузились. У нас уже 7-я, да, лекция?
Примерно.
Ну ладно.
Можно 6.
Нет, по-моему, уже 7-я. Ну, вы тогда закинете потом эти конспекты, а то все. Хотя, может, сегодня занятие тервящих не будет. Ладно. Я просто про конспект. О, смотрите, сегодня повезло. Yeah, so today I want to speak about ramification groups, but we have to do some remarks on different. And ramification. Yeah, so first, how we defined it. So we had, so as usual, we had the field extension. So here you have A is integrally closed, which was important. B is also integral closure of A in L. And what we have, we have introduced the trace map from L times L to K. Yeah, so the bilinear form that was just this was so it came from linear functional. So also we denoted by the same letter. Yes, that was the following to the element A of L. It associates the trace of operator L of A. So here. Well, L of A was the multiplication from L into L by A. Yeah? And this allows also, if you have a linear functional and some product, yes, so that you can define the trace map of AB via just, so you can define the formula that AB is just a trace of AB. You apply the corresponding linear functional. The product of two elements, and this gives you bilinear form, and if L of K is separable, then this form trace is non-zero linear form, and the form is non-degenerate. Yeah, that was our setting, and what was the benefit here? So via this form, we have proved that the following observation that B was, so we have taken B, put some subset inside the AN by choosing appropriate choice of basis. So we put some, let me say, some gamma here that was isomorphic to AN, and via the choice of basis. Here you have just chosen the basis of integer elements. So omega 1, omega n was the basis of L over K. That allowed us to, we had just taken a basis and we have multiplied these elements by some elements from A in order so that omega I are contained in B. Yeah? So such that omega I are contained in B. And this allowed us to do the following. So via this trace formula, you can so on the set of so this things are called lattices. Yes, so they are finitely generated A module. They are called lattices in L. So and finitely generated A modules in L are called lattices. Yeah, so why they are called lattices? Simply because you may think of it as so A can be put as z to the power as z. Yeah, so you can start from integer numbers, and this will, if you have extension of some L, which is extension of Q of degree n, then of course this thing will be just we shall take B and it will contain z to the power n. So that's why they're called lattices. So because they are lattices for A equal to integer. In case if and there is also additional property that we want to have so finitely generated module gamma in L. If you take if one takes the tensor product of gamma over A with K, so this will be isomorphic to L. So it has the highest, the largest set of generators, so the largest dimension of set of generators as possible. But of course it can happen, so it can happen that, yeah, so here you may notice that, so a remark, that so if you are asked about gamma, such finitely generated modules, what can be the type of these modules? And for example, for Z and just if A is a local ring, so A is equal to Z, or A is a local ring, or more generally, A is a principal ideal domain. Yeah, so we have a general theorem that is usually proved on the course of algebra that is so how the module, what is the structure of the modules over A. Yeah, so if M is finitely generated module, yeah, then it can be described as sum, yeah, as a sum of what? So which components? there is a free part, yeah, so which is a in the power r, and r is usually just set to be the rank, and the distortion part, yeah. So the torsion part is just of m is just the set of elements such that there exists f in A such that f annihilates m. Yeah? So so A is supposed without zero divisors. Yeah, so just A is integral domain because we start with a subring in the field of fractions. Yeah, and this more general, more precisely, this torsion part is can be described as the sum of A modulo Fi's, where Fi's are some principal ideals. Yeah, so just, but for us it is not needed for the moment. What we have to see that if you have submodule in the fraction field, then m is just e to the power r. Yeah, so that this means that if m is a subset of L, this implies that m is just e to the power r, and then you can recover what is r. Yeah, so via this via if you tensor it by k over a. Yeah, so you will see that this module isomorphic to A will be just k over r, and this should be equal by our assumption. This should be equal. Yeah, so maybe I shall put gamma here because we just. Yeah, so this, if it is whole L, this implies that R is equal to N, of course, yeah, because here we have the bases. And so this tells you that these lattices have the full rank. So moreover, we have established the following duality. So you can take gamma. Of course, you can consider this operation for any subset, but it is it is just it makes most sense in the case that we have described. So these are the elements of L, such that you take this trace, you take the bilinear form that you fix. Yeah? So bilinear form L, and you just say that the product should belong to A for any gamma that sits in gamma. And of course, what you need from this bilinear form is so that if we want to have the property that we had from the beginning, that B, if you take this bilinear form and apply it to B, then you map it. Yeah, so so it has values in K. Yes, and this is because that trace itself was the function from B to L. We have understood that using integer elements, it was clear that this was function from D to A. And then you see that if you have this gamma inside B, we passed to the dual. Yes, so we can pass to the dual of B. And for modules, you have opposite inclusions because you have, if module is smaller, then there is this number of conditions is smaller, then clearly you have this kind of inclusion. And also you have inclusion that B is a subset of B dual, just because the trace of B1, B2. Yeah, so if you substitute, try to check the property, the trace of two elements, if you have elements B1 and B2 that are in A, the trace of them belongs to A. So you have this kind of inclusion, yeah, so between these modules. And this, if you have free module, so if gamma is free, the thing that we have proved in previous class, that if gamma is free, a priori, without saying, so a priori we worked without additional assumption on the ring A. This was just the remark, yeah, about how the just what happens in when you consider the module over Z, or the just when A is a discrete valuation ring. So if gamma is free, then so free means that gamma is isomorphic. So gamma is isomorphic to an, where n and we assume that n has maximal dimension. So n is just the L over k. So the corresponding degree. And then we have proved that gamma dual is just isomorphic to A to the power n. So thinking of this by taking a dual basis, yes. So by taking eta i's the basis in L, so it was a basis such that eta I omega j is a Kronecker delta symbol. Yeah. So this allowed us to identify the dual thing with a to the power n. So you see that B is contained in an, so B was finitely generated module. Yeah, so this proves that B is a finitely generated module. Generated a module in an. Yes, so in an, which is isomorphic to gamma dual. And by Noetherian property, that by Noetherian property, that this implies that B is Noetherian as the ring. So which is completely non-trivial, and actually if you have the ring, nobody guarantees you that integral closure is finitely so if you start with Noetherian ring, nobody guarantees you that the integer closure is a Noetherian ring as well. So this there is a counterexample by Nagata. So there is famous remark that if B is so if A is Noetherian, just without the assumption that we have, so if you have A in its fraction field of A is Noetherian, then integral closure, integer closure of A in fraction field of A can be not non-trivial. And if you want to if you want to derive the good properties of so one should remark that in algebraic geometry, so remark that if you have A is finitely generated algebra over the field, then you see that, so what can you do? So there is a Noether normalization lemma, so Noether normalization, that tells you that there is the subring of polynomials. So A is without, A is integral, so without zero divisors, A is integral domain. So you have, so this is a subset of A such that these elements are algebraically independent. And this also, so also A is finitely generated module. Finitely generated module over this subring. And this is finitely generated module over this subring, so we can apply our, so finitely generated module means that if now you consider fraction field of A, and so the fraction field of the polynomial ring, which is the ring of rational functions. And so you have A here. So you see that integral closure, you can take integer closure of A into fraction field of A. So you see that the integer elements, of fraction field of A over A are also integer over this submodule, so are also integer over K of x1 xn. This is because, so that all elements of A are integer over this ring. So all elements of A are integer over K of x1 xn. You have criterion, so of integrality. So this implies that you simply were in the situation that we consider. So we just put So we have to see that this is precisely the extension of L. Yes, so that. Yeah, so you have L, K, B here, and A here. Yeah, so if you look at this diagram, this will be precisely this diagram that we obtained, and you see that integral, if you put for here the integral closure of A, which is B, yeah, then you will see that just A will be the integral closure of A will be a Netherland ring. So by previous theorem, A integral closure, closure is Netherland. Yeah, so actually it is finitely generated algebra, but over A. So this proves this property in the geometric world, that we know that always if it starts with a fine variety and normalization is also a fine variety, we know this simply by this theorem, which is completely non-trivial from my point of view. And also, so of course here you have to also in a geometric case you have considered separately the non-separable extension. Yeah, so just but this is done similarly because non-separable extensions are more or less adding square, so more or less adding pth or root of the elements. So just it is not a pain at all here. So also the non-separable extensions should be considered here. So non-separable extensions are considered separately. So so now I want to discuss different, and what we have understood that it was important to consider the following. So we have considered modules n's over L. Yeah, so that's gammas, where M is finitely generated module. So finitely generated a module, and these are called fractional ideals. So such modules are called fractional ideals. And the reason is the following. So if you have just M and you have it is generated by some collection of elements, yeah, so you may take this. You can. So this is finitely generated modules. It is written as just A1 divided by Q1, etc. An divided by Qn. Yeah, so this is inside of so here you so here you may think of the fractional. So here of course so maybe I should write it like this, yeah, so you start with M in the fraction field of A. Yeah. So, and with finitely generated module in fraction field of A. And these are elements of the fraction field. And by multiplying so they are finitely generated, so you can multiply by the common denominator, Q1, Qn, and you get the submodule. Yeah, so just Q1, Qn is the submodule of A. But this is ideal, so A submodule. So which is ideal. So that's why sometimes one takes this part as a definition, yeah, and just so yeah, so I in K is called fractional ideal. If there exists some A such that A times I sits inside the A. Yeah, so that but this is vice versa. If you have taken I, put by multiplication of an element with A, you have put it inside A, then you have an ideal, and from Noetherian property of A, it is finitely generated. Yeah, so when is Noetherian, I is finitely generated module. Just because you can pass, I is just so I is equal to A inverse. So and AI is ideal. Okay. So these notions are more or less equivalent. So they're equivalent in the Noetherian world. And so we can use the notion which that is more convenient for us. Yeah? So this means that yeah. So about our operations, yes. So you see that when remark. Yeah, so when we started Dedekind invariance, so we have considered, so here was prime element, so prime ideal, or generally we have considered I, yeah. We can pass to P inverse or either I inverse, and when A was integrally closed, so A is integrally closed. Yeah, so we we thought of Dedekind the domains here. So we have noticed that P inverse. What about P inverse? Yeah, so just P inverse was proved that first of all it is larger than the initial ring, and P inverse times P, it was just the whole ring A. Yeah, so let me also recall that these are just elements of fraction field, such that Lx belongs to I to A for any x inside I. And so we have noticed that P times P inverse is the whole ring, and the question is, what about P inverse? So can we say that it has some additional properties, so some special properties? And notice that if you have A, which is, so if you put, take an element, and you take inverses, then inclusions will be reversed again for the reason of the number of conditions. And so here you will have P inverse, and that will be bounded by A inverse, so the inverse of the principal ideal. But one can take just by direct calculation, this is just the elements of A divided. So this is just can be identified with A 1 over A times A, and as a subset of L. So this bounds all the denominators of P inverse, and this tells you that P inverse is finitely generated model. So this means that P inverse is a finitely generated module. Yeah, so this is just a fractional ideal.
Is it something like dual line bundle? Is it something like dual line bundle?
Вот, по-русски спросите, что?
Жодные идеалы — это типа линейное расслоение.
Да, это все так, это буквально линейное расслоение, но они как бы обратимые, да, ну то есть как бы с точки зрения модуля, да, это обратимое, ну то есть вы берете, но тут как бы мы работаем с ними над декендровыми кольцами, не забывайте, поэтому тут как бы, ну то есть тут, то есть вообще говоря, не каждый идеал можно вот так обратить вот в любом кольце. Ну то есть тип минус первый вы написать можете, а буквально чтобы вы обратили, это было векторное расслоение, нет. И поэтому, ну как бы вот то, что вот эти вот дробные идеалы, это буквально, да, линейное расслоение, ну как бы аналог линейных расслоений.
Ну вот этот и минус первый, это
да.
Обратное будет?
Да, это буквально обратное. Ну потому что для линейных расслоений это L на минус первый изоморфно от, да.
А тензорное произведение — это просто умножение.
Да, потому что оно как бы без ядра. Ну.
Хорошо.
Yeah, so so that was some kind of motivating reasons. However, I think that this notion appeared much before line bundles have appeared in the literature. What I wanted to say, so the last part of the lecture was the question about different, yes, so that we wanted to introduce different. And notice that, so if you take I, yes, so that, so if you start with our situation, so you have B, it contains A, and we passed to B star, that was, so that contained B, and that was bounded by gamma dual, which was the finitely generated module. So from this point of view, yes, so B star is also a fractional ideal. And so B star it is also B module, and since it is finitely generated A module, it is also finitely generated B module. So it is finitely generated B module as well. So it is a fractional ideal. In B, for B, yeah. I mean, always we consider fractional ideal with respect to the base ring. Yeah, so for L with respect to B. And then you can formally apply the operation B inverse. So you have B that was contained in B inverse, B dual. If you apply inverse, then you have opposite inclusion. Yeah, so you have B inverse here. It is you have opposite inclusion for but notice that we have when we have studied the rings, yes, so B was integrally closed, so yeah, so the property that for B, that B times B inverse, that was a subset of B, this implies that elements B tilde of B inverse are integer, so integer over B, because B is finitely generated B module. And this implies that B inverse is equal to B. Yeah, so for B integrally closed. So this implies that now B inverse B dual inverse is just a subset of B. Yeah? So this is ideal, and this is called different.
Excuse me, how did we obtain that B inverse equals to B?
Ну, смотрите, по определению, B на B инверс, оно должно лежать в I. Это значит поэлементно, что B с волной на B лежит в B. B конечно порожденный B модуль. И у вас есть элемент, который сохраняет модуль. Ну, значит B цел. Yeah. So, finitely generated B module. And of course, this is, I mean, when we're speaking, so this should be always noted. It is the starting point of the theory when we want to say that the inverse of the ideal is a good object, yeah, so that you have to have at least unit element. So that's why we have only option to have B for the unit element in the group of ideals. So you see that this is ideal, and one can ask, can we calculate this difference more explicitly? And so can we say something about this so the structure of the extensions we are knowing this different, and what is more important, so most important here, that is a geometric characterization of the different. So if you have ramified covering, So if you have spectrum of A, and this is spectrum of B, and you have the ideals in spectrum of A where you have ramifications. So E of beta I are non-zero, are not 1. So this different, yeah. So it is now ideal in Dedekind ring. So this different is can be written as beta 1, etc., beta k in some powers, E1 tilde, ek tilde. And the thing is that you can recover this ramification indices from this ones. So the i's are bigger or equal than this ramification indices where beta I runs through ideals of B that are ramified. So ramified means that have non-trivial ramification index. So the benefit of considering such ideals that these indices, this divisibility, so that indices in the decomposition, they bound the multiplicities of the ramification. So by knowing a priori that you have ideal, you know that the set of points, in particular, you see that the set of points where the morphism is ramified, these are bounded. So there are a finite number of ideals that can be found there, and their multiplicities are also bound. And geometrical, it is, so if you know what is relative canonical sheaf, so, sorry, not canonical sheaf, relative Kähler differentials, so the different is annihilator of this sheaf of relative Kähler differentials. So,
the different is what?
the different is annihilator of yeah, so I mean, let me write it. So if you have a morphism of varieties, you can consider the sheaf of relative differentials. And different is annihilator of this sheaf. So just d of BA is annihilator of omega 1 xy. I mean this I want. So here we shall see this after some kind of calculation. And in order to do it, this will be more or less explicitly by the local coordinates, but so I will just do some calculation which is needed here. So, well, calculation of different of d of BA in case when L is obtained of adding only one element to the field. Yes, so you just where alpha is a root of irreducible polynomial f. So
So this could be a map from the conic to predict the line. This could be a projection from map from the conic to predict the flight.
Yeah. So so this yeah. So in our case, we noticed that usually, well, in some cases, we see that the ramification, that extension was obtained only by adding one element. And yeah, so also notice that remark that if you have localization, so different behaves well under localization. So d of b a behave consistently under localization. So if you have, for example, just S is a multiplicative set of A, then if you take different, it is equal. So if you, so localization of different, I'm just saying that you take the corresponding ideal and you consider the ideal generated by it in the localization. So this is ideal in BS. So this is ideal in BS. So this can be obtained as taking localization of the rings and taking the localization. So this is more or less evident exercise. So this just so if then when you localize it, yeah, so you reduce. If, for example, yeah, so when, yeah, so of course it is now tempting to apply this in some special case when you take the principal ideal, take so prime ideal, take the localization set with respect to this ideal, and you obtain the extension BS over AP. So that means that you had some spectrum of A, spectrum of B. So you localize in the neighborhood of P, and geometrically this means that you neglect all the points that are outside of preimages of P, and you are interested only in BI's lying over P. Only they survive after this localization. So your different really just gives you the track of preimage over a given point that is obtained by the localization. But in this case, you know that yes. So if so, in this case, we know that the field is our field is obtained as generated by. So we have proved that it could be BS can be generated by two elements. And then we proved that when so let me say that in this case that we proved that BS can be generated by one element over AP by one element when the extension of when extension of BS modulo B is separable over AP mod P. So we have proved that in this case we can generate by one element. So this condition that this calculation that I want to do is not restricting. Yeah, so just if you want to study what are degrees, this property of writing down the different, so you start with that you can write down the different in case of so in the decomposition of E1 ES and then passing to localization. Yes, we have the same expression for localization. So if I mean the same degrees, yes, so that means that different can have ideals just lying outside of the ideals lying over P. That you have to just keep the ideals beta I lying over P. So just in this ideal corresponding to the localization of the different, yes, so you have to keep when you just localize the expression, so you can calculate the different from the viewpoint of taking localized rings and calculate the different, or just taking the expression for different and localize it. And in order to get the localized expression, you have to keep only beta I that are lying over P and keep the same degrees. Yeah? So that's why you can read of so of the indices we are localizing in different P's. Yeah? So just there will be a different P's for so some beta i's, of course, they map into the corresponding P. Yeah, so there is only one P that is just intersection of Bi with A. Yeah, so this in the different you have blocks of the pre-images that, and you can read of the degrees we are just localizing and taking the same degrees. So let me proceed with the calculation. And so just consider L, which is K, where you add the one element, alpha is the root of F. And so just yeah, so let me do the following. So just take take F and you can do the following. So you can just so f of alpha will be divisible polynomial. So f of x can be written as the following. So just f of x where you divide by the remaining. So g of x. And if you look at if you look at the corresponding polynomial in alpha, so that you can take the product. So just let me put f to be the product via the roots. And and alpha 0, alpha 0 is just alpha. So and you are considering the product over the roots, and you can substitute to this G, you can substitute alpha, which is a product of alpha I is not equal to alpha. And this can be expressed as follows. So you can take the derivative and substitute alpha. So this is just substituting alpha in the derivative. And the proof is just a straightforward calculation that if you take this product and take derivative via Newton-Leibniz formula, then you just have the component where you have x, so precisely this component, so f prime of x has the component of x alpha 1, etc., x alpha n, plus components plus the sum of the products where x minus alpha I, where just from alpha 0, where you omit the sum and the x minus alpha I. Yeah, so let me get rid of the product now. Yeah, so what is the basis? So what is the standard basis of L over just of L over K? Yes, so of course the standard basis is just generated by the powers of alpha. So basis L over K is generated by 1 alpha square, etc., alpha m minus 1. And so our aim is to consider, so in order to calculate different, you have to calculate, so now the ring, so L is generated as a free module, yeah, and so it is, in order to calculate different, it is sufficient to calculate the dual basis. Yeah? So in the argument that omega I in our picture were just this alpha in the power I. So the aim is to calculate, aim is to calculate dual basis. Dual basis at I for this omega I. So and notice, yeah, in order to do it, we have to consider the following. So what is the trace? So how do you calculate the trace of this thing? Yes, so let us recall that trace of beta, it is can be calculated. Yes, so you have set of inclusions of L into algebraic closure of L in the separable case, and then the trace is just applying sigma, so the set of all inclusions to beta. And when you are thinking of sigma, sigma maps, so the corresponding sigma maps alpha to the root, so which is the root of f, to the root of f. So it maps to some alpha I, and it is characterized via this property. So you have to just apply this formula, and let us do some kind of additional observation that just consider the following. So write down xi as a polynomial. Just a polynomial in x. And we can write interpolation formula, Lagrange interpolation formula, in the roots of alpha I. So Lagrange interpolation. Formula in roots of alpha I. Yeah, so how to write it down? Yeah, so this is written as follows. Yeah, so let me put it as the polynomial g. Yeah, so that means that you have to calculate g, well, h. Yeah, so you have to take the values of the function and to write down the corresponding monomial where just, so you are evaluating h or in the corresponding root, write down the monomial that is not vanishing on the root. And divide it so to have this monomial equal to, so this polynomial has to have the property that in all roots except the given one it is 0, and in the root alpha I it has precisely value alpha I. So you are writing down, you have to divide it by the corresponding value. And this as a function, it is just x of I. Yeah? So, how to write this, how to rewrite this? So we can rewrite this polynomials. Yeah? So we can rewrite it as follows. So this is h of alpha. Well, it is h of x. Yeah? And this can be rewritten in terms of f. Yeah, so this is just the polynomial f of x divided by x minus alpha, and divided alpha I, and divided by f prime of alpha I, of alpha, of the corresponding alpha I. And yeah, so and you have to take the sum over I, and it is just h of x. So if now yeah, so now we have to see the following. So here, so if h is precisely so if h is precisely h of x is the power, yeah, so you have to just in the summand So the sum is taken over the roots alpha I. Yeah? So all over roots. So if you take, for example, just alpha I, this will mean, so alpha j. Okay, sorry. Let us see. Yeah, so if you have, so here you take xg. So you want to have the root alpha j, and you want to write down the dual. So dual basis. And if you want to write dual basis, what you have? So notice that just that if you write down the conjugates to alpha I, these are just alpha I j's. Yeah? And what is standing here? So here you have a polynomial f of x, which is just divided by x minus alpha. It is some polynomial in roots of alpha. Yeah? So if you open the brackets, this will be a polynomial in x and alpha. Yeah, so meaning that it is you have x n minus 1 plus beta b of alpha, the corresponding coefficient x n minus 2, etc., b0 of alpha. And if you and here you have also the derivative, so it is 1 over, you can write down 1 over f prime of alpha. So just what is, yeah, so let me write down that again. You have this kind of, so you can write down f prime of alpha times this polynomial g x alpha, and of course writing down, so this polynomial, it has coefficients that are just polynomials in alpha. You're just you can divide it formally and write down formal expressions for these coefficients. So these are polynomials in alpha with actually coefficients are integer or rational, and yeah, so of course there will be on one side just yeah, so one have to see precisely that something about these coefficients, yeah, because we want to have the integral basis. And if you apply sigma to this expression, this is simply substituting alpha I in this expression. Yeah, so this is simply writing down 1 over f prime of alpha I, alpha I, and upstairs, yeah, so you are writing down g x alpha I, and you are just writing f of x divided by x minus alpha I, and writing down this derivative. So you see, I mean, of course it is clear that it is just, I mean that you are just substituting alpha I in this expression, but what is written actually here? Yeah, so you are writing down, if you open the bracket, so I'm saying that you should write, so I just needed this expression, so the sum before written before is the following. So you are writing the sum of that just we have written is just the sum over all sigmas, where sigma was applied to alpha j f of x divided by f prime of alpha x minus alpha. So this was, and what was standing here? So this was a calculation of trace of this element. So this was calculation of trace of this alpha j fx f prime of alpha x minus alpha. And I'm just saying that I'm looking at this expression for the polynomial. Yeah, and what is the answer for this trace? Yeah, so as a function, it was x. So it was x in the power j. Yeah. So as a polynomial, it was x in the power j. So if I open the brackets here for the trace, what I'm getting, yeah, so it is just, and trace of this, I can think of taking trace coefficient-wise. Yeah, so if I have a polynomial, yeah, I can take trace only of coefficients. And if you, here as well, yeah, so here when we calculated trace, in the left-hand side, we have written it as a trace, thinking of these polynomials as just you are writing the polynomials with some coefficients and you apply trace coefficient-wise. And if you open it in terms of, so if you look what is this bracket, it is just alpha j, you multiply it by 1 over f prime of alpha. And here you are writing down polynomial of x and alpha, and when you apply trace, you get xg. And if you open the brackets, that means that you are writing down alpha g, you are multiplying it by 1 over f prime of alpha. And here you have coefficients xn minus 1 plus beta n minus 1 of alpha, xn minus 2, etc., beta 0 of alpha. And you see here that it is equal to trace, so it is just xg. So what you see that if you take trace of it, so you have to take trace coefficient-wise. So that means that if you take one of the coefficient, so this will be, so you have compare this side and this side, and coefficients of this polynomial are just traces of alpha j 1 over f prime of alpha beta k of alpha. Yeah. So you can compare, and you are writing down xk and you are writing down the sum over k. So this means that just saying that it is xj, it is just saying that all coefficients in this polynomial vanish except this one, which is 1. So you get delta Kronecker symbol for beta k. So this means that beta k of alpha is dual basis. Is dual basis to alpha j. So it is just Lagrange formula, right interpretation of Lagrange formula. And yeah, so what is so what about beta k? So actually, yeah, so we have constructed this basis, but we are not interested in the basis itself. We are interested in the ring generated by the basis. So, so of course, we have much more information that we needed. So we have to consider ring generated by beta k of alpha, or even more, ideal generated, yeah, so by this guys, and but actually we need only the vector space, because the dual object is just the vector space, yeah, so that vector just module we actually need not the ideal, but only a module. It is sufficient to generate an ideal that will coincide with just a module, because we have established that if you have a free module, then the dual to the free module is a free module generated by the same basis, so by the dual basis. But we have to realize what is BK, but notice the following. So just this is just by definition that you have to calculate. So f of x. Yeah, so you are just want to write it down. So this is a polynomial x n minus 1 plus beta n minus 2 alpha x n minus 2, etc. plus beta 0 of alpha. You are multiplying it by x minus alpha. So let us write down explicitly the system of equations. Yes, so that you have to write down ck, well, ak in terms of the corresponding beta. Yes, so that ak is written as just you are writing down beta k of alpha plus alpha times beta k minus 1. So you see that if you recalculate beta k from the viewpoint of coefficients of A, there so you have triangular system. Yeah, so that just beta k of alpha is just ak minus alpha bk minus 1 of alpha. So all betas are, if you look at the linear span, it is the same of the, so that they are they're polynomials in alpha I with integer coefficients. So,
Excuse me, why do we have n minus 1 bk's?
ну в смысле я с нуля там начал,
We
ну
need n, right?
где?
So our initial basis 1 alpha squared had n.
Не, ну многочлен степени n, f многочлен степени n.
Да.
Ну я зря там альфа 0 написал, надо с альфа 1 был начинать. Ну в смысле вот ну как бы вот тут все-таки я глупость сделал. Да, даже не, ну вот не альфа 0, а альфа 1 это, да, нужно. То есть, надо было их с единички нумеровать, а не с нуля. Ну, то есть вот в произведении. Да.
У нас бэшек мало. У нас бэшек на одну меньше, чем нужно.
Бэшек, почему? Ну, у нас степень f-то как бы, ну, f степени m.
Да, значит, нам нужно n бэшек. Мы же хотим, чтобы это был базис свойств.
Ну, еще просто константы там есть.
А, единицы.
Да.
Ну, хорошо, да.
Просто последний многочлен, ну, у вас есть вот он, beta, ну, формально я должен был написать, что вот это beta-1, но у меня тут рука не поднялась, да?
Хорошо, да.
Там, кажется, ну, БК и БК-1, выражение АК надо местами поменять.
Да, действительно. Ну, то есть они как бы, ну, да. То есть, да. Ну, потому что мы с единицы начинаем и начинаем считать многочлены. Вот, ну и, соответственно, тут как бы, да, БК, теперь...
Там надо что-то не то.
А?
Там что-то
Не, мы наоборот, мы как бы БК минус 1 через БК выражаем, да? Ну, то есть, как бы самое сложное, это самый младший коэффициент, он будет многочленом самой старшей степени, да? Yeah, so this formula gives you that just BKs are integer polynomials with coefficients in alpha, and they are just so this is degree 0, degree 1, etc., degree n minus 1 polynomial. So you see that that what is spanned by BI is just BI spans BIs of alpha is just the span of this basis is just 1 alpha etc. alpha n minus 1. And this, if you look at the corresponding formula, so we have to generate the ideal by this coefficient, but there is additional coefficient, 1 over f prime. Yeah? So you have to write down the ideal generated by the dual basis. So this is just, I have to write down 1 over derivative. So formally, the dual basis is 1 over derivative of alpha bk. So since these guys generate the same thing as alpha j, so the dual basis is 1 over f alpha. Yeah, so that full dual basis. So this means that span of the dual basis, so vector space, well, A module spanned by the dual basis is 1 over f alpha, the span of BIs, which is just 1 over f alpha times b. So just, and so you see that when this is a fractional ideal, when you see that you need to invert it. When you invert it, then you get the principal ideal generated by f prime of alpha. Yes, so invert. So just to get B dual inverse is just a principal ideal generated by this f prime alpha. Понятно? Ну, давайте перерыв сделаем небольшой. Я расскажу про группу ветвления.
Перерыв сколько?
Ну, давайте 5.
Short sequence. If you have map of varieties, right? That's why you have a short sequence 0. I don't remember.
So this is not smooth.
Yes, not smooth.
So it's very simple.
It's exact.
In R you have more map from Shiva differentials.
Yes, but I don't remember.
Here, yeah, you have it here, and then you take Kurbach Shiva differentials here,
Yes.
and then two relative Shiva differentials.
Yes, that is secure.
It's part of 500 of Shiva relative Shiva differentials was very simple. Differential.
Yeah, so easier, easier, but yeah, so you have to, yeah, you have to consider I mean formally just yeah, so you have to consider derivations which are trivial on
So derivations here which are
which are trivial on A, and this is just the defining property, and so that you know that
but we can't say push forward of differential. You can say pull back of
no, so you are considering, yeah, no, so what is just that? So what is defining property of the sheaf of Taylor differentials? It is just the cones to this sheaf.
From some other modular.
Yeah, so so if you want to write down so that write down the differential from the module,
And then we have
then
universal
you have
property.
universal property that just this is fixed differential. This is just any, and this is just a given one. Yeah. So and for example, you can if you want to speak of the tangent bundle. So this is differentials. It is classified from differentials to differentials. So the derivatives from the yeah. This is just from this description. This is just dual module of this absolutely lemma equal to b. And then from dx is just and you have to just it is convenient to start with so then you have to do the following. So you have to take the write down generators, so it is generated by b1 so bt over a. So possibly module some relations. So and if you want to calculate this universal sheet, then it is clear that so the generators should be b1 bt, and the what are relations? Of course, if you know that to 0 and b, then you know that when you map it to the module, it will be also 0.
Yeah.
So you just need, so these are just repetitions.
Why would you do zero?
Hmm? Yeah, so you are just writing down explicitly f of i's of b1, bk. Yeah. You have to take the d of b1, bk formally. Just by line. Or just, or saying that it is just partial derivatives d of fij modulo the corresponding variable.
Yes, okay, so in this,
This j, and here you are writing down db I as generators.
so in this case we have just one relation.
Yeah,
So
yeah.
So the relation is just y squared equals x squared minus 1.
Yeah.
So the relations will be, we have dy and we have dx, and we take quotient by the relations df, dx.
Notice that it is, you are taking point relative differentials, so over one. So you need only one variable in the expression.
So it will be dy.
No, I mean you have to, so you of course considering the following equation, yes?
Yeah.
But you are considering the
kfx.
KFX, yes, so so that means that this is variable.
Yeah, so we have dy.
Yeah, so it's generated by dy, and you have to say what are relations are obtained by dimension.
So it's dy equals
Просто любой модуль
1 minus x.
No,
Let's
do
do
just you are just the derivation should be 0 with respect to a.
And a is kfx.
I mean, yeah. So it should be 0 on a.
Yeah.
So the d of x should be 0. I mean, so you're thinking of, I mean, so so this derivatives. So it is important that this is dp over a. So here you are writing down dp over a, but here b over a on a is equal to 0. So that means that we have differential forms dx.
Yeah.
So yeah, and but in dx dp of x is equal to 0.
Yeah.
So I mean when you apply it to dx, it is equal to 0.
So we just get dy.
Why do what? It is, yeah, it is a question. So why is it correct?
Okay.
Yeah, so one should think of it, and in general you have expansion that you have dB of over k. So we can, so differentials on the whole, we can restrict it to the fiber. So it is same as dB.
So here then.
Yeah. And yeah, so and this is just restriction of the fiber. So you get relative differentials. And in here you have the pullback, so the differentials on A can be considered as the differentials on B. We are the pullback. Just writing down the pullback on the
Yeah.
A1. So this is suggested, and this is not. This is just
Because it's
in general.
because it's not smooth morphism.
Yes.
And then it follows immediately that the different here is just generated by y because it's an equilibrium. So the different is generated by y. Okay, nice.
Я пишу
А
по-английски.
что там за пример
Так,
лица, который не очень
По-русски
одного
еще думать, как
Вот.
пишут.
Это я не помню. Но причем это не так просто. Вот такая методология.
Вот меня удивило.
Ну, поэтому я это подчеркнул. Но просто это нас смотрел когда-то, но это все равно это отдельная
Я
вещь.
пишу.
Есть книжка контрпримеры по анализу, есть книжка контрпримеры по
Место осталось. Потому
Отлично.
что я хочу порадоваться.
Хочется, чтобы она была.
Понятно. Ну что, давайте продолжим. Yeah, so let us continue. Yeah, so now, so now let me consider example. And this will explain why different is important for us. So that recall that we had if you have A is a discrete valuation ring, so we can consider total ramified extensions. And they are just they are defined by the following. So you just have B is discrete. So here you have uniformizer pi, for example, and you have if you have omega uniformizer of of B, so the generator of maximal ideal in B, then you just write down equation. So for this omega, and on one of the previous classes we have found out that A0, so all AIs are divisible by P. And A0 is not divisible by P. And now we have so here you have only one ideals, so only one ideal, so the different D of BA in
I think A0 is not divisible by 2 square.
да. Спасибо. And if you consider D of BA, it is just power of some, so it is ideal of BA, so it is just power of some B, so it's power of B. Of beta. And you have to calculate what is this S. But in order to calculate it, you know that it is principal ideal. So since your extension is generated by one element, so B is obtained by adding omega to A. So the root of F. Yeah, so it is just extension generated by, so it is ideal generated by applying derivative of F to omega, and you are just, you have to write down what is this derivative, and how you can just calculate the. So what is the maximum power of b that can divide the derivative? So let us write down derivative. Yeah, so what you see here, yeah, so again, you have the following picture that, what you see in this expression, that, so if, so again, we can take valuation with respect to omega or with respect to p. Yeah, so let us say that, let us take the valuation of omega equal to 1 over e as usual. Yeah, so that will be the valuation if you think of it with respect to ideal p. And what you have? So here you have valuation is divisible by e. So yeah, so here, yeah, so let us start of characteristic zero case, yeah. So characteristic of k is equal to 0, yeah, so of k. Yeah, so then you see that we can neglect all coefficients, all ai. And only this, just only, I mean, you know that they are not, yeah, so, yeah, sorry, we cannot neglect them. Just a second. Yeah, so what? Yeah, so what you have to notice that if you have e minus I, e minus 1 omega e minus I. Yeah, so if you take a valuation with respect to p, so you have to look at, you have to understand the following. So the valuation of this part is, so these are numbers, yeah, so this is divisible by e. So these are elements of the initial field, yeah, so that valuation of x, just where x belongs to k is integer. Yeah, so and if so, this means that this is so this is integer valuation, and this valuation is precisely e minus I divided by e.
It should be e minus I minus 1.
Yeah, yeah. Mm. But what is important here that they are pairwise distant. Yeah? So the valuation are pairwise distant because this is just in if you think of this as an element of Q mod, well, in Q mod Z, so these are different numbers. So they are pairwise different numbers. Different numbers. And so you have integer number. So the valuation is integer plus so integer minus the number I plus 1 divided by E. So these elements are pairwise different, so these numbers cannot be equal. Yeah? So this implies that if you have the valuation, so if you have the element, well, x, which is x1 plus etc. x k, where valuation of xi is not equal to the valuation of xk pairwise, yeah, so that valuation of x is just minimum of the all valuations. Of okay, and you see that now what is yeah, so what is minimal? So if you analyze this picture, yeah, so if you analyze this element, suppose yeah, so what you know that you know at least that the different is the valuation of different is bounded by the coefficients of the polynomial. So corollary that you know that S is bounded, it is less or equal than E times valuation of mu P of S is bounded by the minimal of the valuation of mu P E minus 1 E minus I mu E minus 1 times E. Yes, so you let me write it down beta here. Yes, so valuation of beta is valuation beta of omega is equal to 1, yeah, by our. So S is just minimal of these valuations. But notice that if you want to compare these valuations, suppose that E is not divisible by when E is not divisible by P, where P is the characteristics of the field. So P is characteristics of K. Then you see that you have to compare valuations of omega E, so that E omega E, so E doesn't play a role in this valuation. So you are looking at the remaining terms, but in the remaining terms, this is, if you want to compare what is minimal, so E is not divisible by P. Yeah, so notice that if you have characteristics P, then just yeah, so you have the number which is sorry, here just P is characteristics of characteristics of P. Yeah, so if this is not, of course, divisible by P, and this means that just so if you consider this kind of elements, then you see that these coefficients, so here the valuation of P is greater than 1 of the, just at least it is greater or equal than 1. And here if you compare the difference of E and E minus 1, then of course the difference of this valuation and this one is smaller than 1. Yeah, so that nu of omega e minus minus nu of beta of omega e minus I minus 1. Yeah, so it is equal to I plus 1 divided by e. It is smaller than 1. So you see that this element has minimal, sorry, here this one. Yeah, so this element has minimal valuation. Yeah? The difference is just I divided by e, which is less than 1. So this means that this has minimal valuation. So S is equal to e minus 1. Yeah, so this shows that first of all, this the valuations of in the different are bounded explicitly by the coefficients of polynomial, but if it is not just in the case of good characteristics that when it is not doesn't divide e, then you see that simply S is just equal to I minus 1. So this is this gives you the for example, in characteristic 0, this gives you a very good estimate for the different. Yeah, so that you know that different is just divisible by e minus 1, where e is the ramification index. And you know the ramification index explicitly for the different. So otherwise the ramification index can be a priori smaller. Yeah, so that, but in any case you know that ramification index minus 1 divides the degree of the different. Yeah, so the corollary that the ramification index minus 1 is less or equal than index in different. So that gives you bound. Gives you bound on the ramification. So different itself. So existence of different gives bound on ramification indexes. And proves that there is only finite number of them. Yeah, so, okay. So let us pass to the next topic. So the question is, can one have a more precise estimate in terms of the groups? And one can have some, because this some kind of, the estimates that we have obtained for ramification indexes are not very good because they are not defined intrinsically. Yes, so you are considering minimal polynomial. It is not the thing that is given to us with our object. I mean, it is not written in terms of ideals, etc. So it is not very good object from the viewpoint of functoriality. And now just I want to discuss ramification groups. So ramification subgroups. Of Golar. Yes, so now we assume that our extension is Galois extension. G is a Galois group of L over K. Yeah. And so here you had the ideal P, here you had the ideal beta lying over it. And we have considered a ramification group, G of beta. So this is just the stabilizer of beta. So this allowed us to, so notice that Galois group acts transitively on the set of ideals lying over P. So you have beta I, so G Galois group of L over K acts transitively. So just ideals lying over ideal P, and so you can consider stabilizer, and so the index, so let that be ideals beta 1, etc., beta s. Yeah. So you have a ramification index. It is the same E of beta. It is a ramification index. And F beta is inertia index. It is again the same now for all ideals lying over your given ideal P. If so you have also the following. So we have the formula that says that the degree of extension is just S times E beta times F beta. And so which is just the formula of the sum of E beta I F beta I. And so the index of G is beta, and we have also the map from G beta. So G beta acts on the field. So there is a map of G beta to automorphism group of the field B over beta, because beta preserves. So G beta preserves the ideal beta and acts on the ring B, and this is just it maps to automorphism group of this thing, and we have learned that this is normal extension. So normal extension. And the map is surjective. Yeah? So you can consider the kernel of this map. So kernel of phi. It is called inertia group. So this is the subgroup of beta that what it is. It acts trivially on the field beta mod beta, but you can ask the further properties. Yes, so I beta can act non-trivially. Yeah, so I actually notice that inertia group is normal subgroup. Yeah, because it is just a kernel. So this is normal subgroup. And also you know what is so G beta modular I beta. It is just automorphism group itself. Yeah, so this is just automorphism group of this ring extension. So if you know that it is separable, for example, when AP is finite field, so then it is just Galois group. Yeah, so that when just extension is separable, it is Galois group. Of corresponding extension. So inertia group can act non-trivially on beta modular. So on, of course, G beta it keeps beta square, all powers of beta. Yes, so that it can G beta keeps the series beta square, beta k. So it keeps this flag, and this means that it keeps the flag, but it can act as so when you have the flag of subspaces, then of course. Notice that in our case, when you just pass to when beta is when b is discrete, so we can pass to the following. So we by keeping a, so you can first localize it. So this.
Включение в ту сторону, кажется.
А?
Включение.
Да. So you can localize it, and then you can localize when you are speaking about beta, then you can localize b by beta, and now you can think of the Galois, so the part of the Galois group that just keeps track on this object is of course the composition group. So this dB acts on localization. And this and yeah, so now we can just think of and vice versa. If you have this extension, tautologically the Galois group becomes, I mean, when this is discrete relation ring, yeah, so that in the case where this is discrete relation ring. So this you have only the composition group. Yeah, so it is coincide with the Galois group for trivial reasons. Yeah, so if you have Galois group of B beta over AP, yeah, so of the corresponding fraction fields, this is the composition group. For trivial reasons. So the idea is to start refining the filtration. Yes, so that you can. So inertia group can act trivially on. So it acts trivially on a B mod beta over the smaller subfield, but it can be act non-trivially on B mod beta square. Yeah, so I beta can act non-trivially here. So you are defining the following filtration on the set. So you are defining the function on the elements of your group. So let me put IG. IG is the function from G into integer numbers, and it is just the following. So it is just maximal k. So E of G of sigma. So for the element sigma, it is maximal k where sigma acts trivially on B modular beta k plus 1. So you consider, so you know that, sorry, so this is a map not from Galois group, but from the composition group already. Yeah? So you start thinking of the composition group. It fixes all powers. So you may consider so for each element of the group, you may consider the maximal power of k where sigma acts trivially on beta. Yeah. So so here just we have acts trivially for. I think there should be a k plus 1, but maybe just I have to look what is G0. I mean, G0 is the decomposition group. Yeah, so G0 should be the decomposition group. So, I think so here we don't need 1. Yeah. That's trivial. Yeah. On mod B k. Yeah. So this has several properties. Yeah. So that so that means that you can compare. So just this can be said that we can compare either the following things. So we can compare the valuation of sigma x minus x for any element. Yeah, so for any x inside beta. Yeah, so this and the sigma belongs to GIs. So GI is so this means that so this is x plays role of identity map. So this means that sigma x is equal to x modulo beta I. Yeah, so that means that the valuation should be bigger or equal than I here.
А что такое GID?
Что?
Ну, там слева сигма из ГИД.
Это определение, вот, ну как бы, да, если у вас есть вот эта функция, да, что вы можете записать GIT, это множество элементов сигма из G-бета, да, для которых фильтрация, ну, вот эта функция больше или равна и от бета x больше или равна и. То есть это вот такая убывающая фильтрация. Ну, на группах. То есть как бы чем больше и, тем меньше таких элементов. То есть, ну, по-другому... sorry. Слушаю. Yeah, so just you can rewrite this thing, yes, so that saying that something is trivial, yes, so you can rewrite it in terms of the corresponding valuation, yes, so meaning that it acts trivially modulo beta k means that sigma x is x modulo beta I. So that means that the valuation of the difference is bigger or equal than I. Then you can ask this for any element. But it is sufficient because you have discrete valuation ring, so this is sufficient to claim, to check on generator. I mean, this property is sufficient to be checked on generator because phi is homomorphism. If something is polynomial on on the set of generators, is phi on generators x1, xk. Because if you look at the corresponding polynomial, you just applies a sigma to coefficients, and this is just because this is bigger or equal than minimum of the corresponding valuations. So, for example, it can be checked. For example, when extension is separable, when B is generated by one element, it is checked on the generator. So the next, so this this gives you the corresponding properties. So yeah, so this filtration, yeah, so of course this filtration behaves well when you restrict it to subgroup. Yeah, so when you have H is a subgroup of G, so this filtration behaves consistently. Meaning that if you want to define HI, it is just intersection of GI and H. But the problem when you just so you have the filtration of the spaces, yes. So that the question is that when you have, so suppose H is normal, By the way, so just here, yes. So inertia subgroup is just G1, yes. So G0 is the composition group. Inertia subgroup is just G1 here, yes. So that remark that I of beta is just G1. So G beta is just G0 here. And then you thinking of this, so G beta is just some subgroup, yeah, so but now, so at least if, so G beta is a subgroup, but if you think of the further series in G beta, yeah, so that what is good about this filtration? So that all just remark that if you look at GIs are normal subgroups, normal subgroups. Just because if in G beta, yeah, so just the normal subgroups in G beta. Just because G beta it keeps the corresponding filtration, yeah. So if you conjugate, and so that means that GI is what? So you take sigma, so you take the element, and so you compare. So x was so you compare x of and sigma x modular some filtration bi. If you have some automorphism that so some automorphism tau, for example, it can be written at the conjugation, but it you can apply it to the automorphism of tau to this equality. So the automorphism that induces the just so if you have automorphisms that you can apply it to be to x and to all objects here, and it if it keeps the filtration, then just it also should yeah. So just better to say that if you have tau that is inside the G beta. Yeah, so if you apply just so you have this kind of filtration, and you can apply tau to it. Yeah? So you can apply tau, and tau fixes BIs because it was in G beta. So you see that tau sigma x is equal to tau x modulo beta I. If you write that, but this check is for any x. Yeah, so this check is for any x and beta. So you can put y equal to tau inverse of x, and this allows you to write down sigma tau inverse tau of tau of just tau of x. Yeah. This holds for any x. So let me write down sigma belongs to Gi if this holds for any x in it holds for any x in B. So put y equal to tau x, and you may write this tau inverse of y equal to y modulo beta I. And this is precisely the property of being in the corresponding in the corresponding filtration part of the filtration for G. Yeah, so that means that tau sigma tau inverse belong to Gi. So this proves that the groups are normal. And also, it is interesting to write down different in this setting. Yes, so that just also why this group, in particular, why these groups are important, because d of beta A can be expressed So I mean the different is just the power of some ideal beta, and it can be expressed in terms of orders of GIs. And how it is done, it is just as follows. So you have to take. So again, we have so B is generated over A by one element. By X. So F is minimal polynomial. And now we are writing down so we have to calculate f prime of x. Yes, so we have to take valuation. So valuation of f prime of x with respect to beta. But the minimal polynomial, since we have the action of Galois group, it is just product of so f of t. Yes, so f of t minus sigma of x, where sigma runs through all Galois group. Yeah? And but here your so in our case Galois group is also decomposition group. In our specific extension, and you look at this valuation and notice that f prime is just the product, so f prime of the root, so just f prime of the root x is just the product over all elements x minus sigma of x, where sigma is not equal to 1. So this is a valuation of beta of this product, where x is now generator. But notice that so here you are writing down now here you are writing down it is just a sum of the valuations. And you are writing down specifically, so you are looking at the elements which belong to, so the valuation of generator is precise. So in order to understand to which group sigma belongs, you have to just take the generator and calculate the valuation of generator. Yes, so that sigma belongs to GI. If and only if, so x is equal to sigma of x modulo bi for x generator. Yes, so for x generator. So precisely the element that we have taken here. So this is just I is just the valuation. Valuation of beta of x minus sigma x for generators. And if so, what you are summating, you are summating the number of elements with the valuation precisely I. So you are summating the number, and these are the value of the valuation. So you are summating I times gi minus, so the number of elements in gi minus the number of elements in gi minus 1. Okay. And this, and we are just yes, so you just are opening the brackets, and if you are opening the brackets, then this terms of the form, so gi minus 1, it also, да, тут как бы у нас убывающая фильтрация, да, GI plus 1. Yeah? Ну, то есть, как бы у нас ну, то есть, нужно взять те элементы, которые имеют в точности фильтрацию И, а у нас она убывающая. То есть, so if you open the brackets, then you have minus I times GI plus 1 in one bracket. Yeah? I develop times GI. Yeah, so will be cancelled with the sum of, so you have I plus 1 times GI plus 1 minus I plus 1 times GI plus 2, etc. So if you open the brackets, yes, so that these terms will be cancelled. So this is more or less the sum of GIs, but but this term that you have to get rid of unit in the sum, it gives you that you have to subtract 1 at each term here. So just the following sum. So just I mean correct term. And this will be just an exercise to do it more precisely. And also, yeah, so why these groups are important? Also, because you can, via these groups, you can consider the structure of the Galois group. Yeah, so that this is the following observation that, so let me write it as the proposition. Yeah, so, by the way, so what is the benefit of the formula, of this formula, that we have written the ramification index, yeah, so that the valuation of different in terms of purely in terms of some objects related with, so this is not, so these are related explicitly with the canonically with the fixed ideal. This is independent on any choice of specific equation used for ramification, to define the extension. Yes, so to define totally unramified extension or whatever. This is just this direct calculation. And why just the yeah, so why this is important? Yeah, just because you can do the following, so we can. Yeah, so also we can yeah, so also we can just when you have this extension. So just when you have this extension, yes, so we have Galois group of Galois group of L over K. So here you have G of beta. Here you have I of beta, and you can consider intermediate extensions here. So you, with respect to these subgroups, yes, so that LG beta, L of I beta, yeah, so I smaller, sorry, so the smallest group gives you the largest extension. So you are having Li of beta, so you having here L G of beta, and you are having K. So now what can be said about just about several extensions? So, for example, what you know about, yeah, so you can also think, look at the corresponding rings and the corresponding ideals lying over. Yeah, so that you have A here, you have, let we call B G beta, B I beta, and here you have B. So, and here you may think of ideals lying over this thing, so P. So here you can look at the corresponding beta, so intersection of beta with LG beta. So you can think of the intersection of beta with Li beta, and so here you have beta. So notice that just so what about the types of these extensions? So notice that, for example, G beta. What is index of L? So if you look at the index. So of course G beta over K can be not a Galois extension, but the index of this thing is just this is a Galois extension with exactly the order of B, so this index is just G modulo G beta, so this order. This is just order S. And one can start considering indices, so ramification, one can ask where in this case. So also you have, so N is obtained as E, F, and S. And if you have corresponding extensions, so let me put it on this next page. So if you have separately K and you have intermediate extension F here, so let me say that you have three rings. You have the corresponding ring of corresponding field of fractions. So here you have ideal P. You can take ideal beta lying over it, and you can take ideal gamma lying over beta. Yeah, so you can. So you see that beta is just obtained as gamma intersection with B, and just you are writing down gamma intersection of B with B, and you are writing down P is just the intersection of beta and A. So you can ask about the corresponding ramification indices. Yes, so you can ask about E gamma over beta. You can ask about E beta over P. Meaning that if you do the following, if you localize with respect to P, then with respect to B, and then with respect to gamma, yeah? Or you can start by localizing with respect to gamma, everything, but you localize A and B with respect to the intersection of the complement to gamma. Yeah? So A you change to AP, B you change to B beta, and C is changed to the corresponding localization of gamma. You see that in these ideals, beta, P times B beta will be expressed as beta in some power. So this is precisely the ramification index of beta over P. And this gamma, so if you lift beta to C, it will be expressed as gamma in the corresponding ramification index E of gamma over beta. So it is clear then when you lift P to C, so this will be expressed as gamma, it is expressed as the gamma of the corresponding ramification index of gamma over P, but it will be a product of these two ramification indices. And more generally, you can, so you also can keep track on F. so you have extension, just you have f gamma p, so you also have the same for the ramification and for inertia indices. This is just for the trivial reasons that just you can take the extension C modulo gamma, it extends B modulo beta, and this extends A modulo P. And the degree of this extension is a product of the degrees of intermediate extensions. And this properties tells you that in our picture that I shall rewrite here for the composition groups here. So if you take L modulo inertia group, L modulo decomposition group, and K, then you have to decompose N, the total extension, in terms of E beta, F beta, and the number of the ideals over it. And it is, one can see that this degree of extension is precisely just L d beta over K. It is precisely the just the number of elements in the orbit of, this is just G over D, so here I have to note it by D, so here we have, this is just the order of the Galois group modular G beta. So this this is the number of elements in the orbit. Yes, so this is, so the prime ideal form the orbit. So prime ideals beta form one orbit. So this number S is just the number of elements in this orbit, and so one notices that this number of elements precisely this extension. So one can guess that if you want to write down S as so the corresponding just you have to write down the degree of this extension in terms of the corresponding letters for this extension. And one can guess that here you have corresponding ramification, it should be equal to 1, F is equal to 1, and the S is equal to this given S. I mean, it is a guess, it's not a proof yet. It is just we have noticed that the order of the group is S, and one can guess that ramification and inertia subgroups do not occur here. And what about this extension? Yeah? So this extension is, so how many ideals? So you can think just, yeah, so already, so G fixes your ideal beta. Yeah? This means that if you take, so in this field, G beta, so you are thinking of, just G beta is you may think of the following. So just so take here. So you take the ideal that is obtained from beta by this intersection. Yeah. So you may look at so here this ideals lie over P. Yeah. And you may look at the ideal here. Well, here you have ideal beta in L. That is lying over this ideal because it is in particular lying over P. Yeah?
Там включили в другую сторону.
Да. But what I have to say that so there is important thing here. Yeah? So that if you, by definition of G beta, yes, so you know that Galois group, so G acts, so the Galois group acts, so the Galois group of extension, so and Galois group of extension L over L G beta, which is precisely G beta, acts transitively on the set of ideals, transitively on the set of ideals beta I lying over beta intersection with L G beta. But in particular this beta,
А почему это?
это любая группа Галоа действует,
Да, но это если у нас расширение Галоа.
ну вот это расширение Галоа, вот это расширение. Ну, расширение Галоа, они наоборот, они вот ближайшие к большому полю. То есть, ну как бы, а вот эти факторы, то есть маленькие, ну как бы вот исходное маленькое поле, вот большое, вот расширение Галоа, которое есть. Вот, so it is acting transitively on the set of ideals lying over it, but in particular, these ideals, so beta I are ideals lying over P. Yeah? So also lying over P. But G beta is the stabilizer, stabilizes beta. So this means that this is precisely, this is unique ideal line over it. So this means that beta is a unique ideal lying over beta intersection with L G beta. This is first part which is important, and the second part. So I'm completely out of time, so maybe I shall comment on this on the next class. This is yeah. So what I want to say that suppose your extension of the field of quotient field is separable. So the idea is the following. So here, so this extensions, so this decomposition groups and inertia group allows this to subdivide in three parts. This is totally ramified. This is non-ramified, and the extension is done only on the field of quotients. And this part is just over one ideal. You have several copies of the same ideal. So this makes the picture geometric.